Okay, so before we begin the proceedings, we acknowledge the traditional owners and custodians of country throughout Australia and their continuing connection to land, waters, and culture. We pay our respects to the elders past, present, and emerging, and extend that respect to Aboriginal and Torres Strait Islanders who are present here today. So today it is our first seminar of the year. So I wish everyone has had a very nice break or vacation. And it is our honor to introduce Patrick Group, who is the speaker today. And he is currently a postdoctoral fellow at the University of Melbourne. He obtained his PhD in applied probability, and it is a joint PhD between the University of Queensland and Aarhus University. So Aarhus University is a very, very prestigious university in Denmark, and Patrick was supervised by Søren Espersen and Phil Pollard. Okay, so personally, I really respect Søren Espersen because he had a book, Rune Probability. So that is actually my research area, and then a number of academics in this school is also working on that as well. And the research topic that Patrick is working on include a wide variety of topics in mathematics, statistics, and computing. And I think Patrick is also a software engineer, and he has also working experience in Lyon in the Institute of Science, Finance, and Actuary. I don't know whether I translate that properly because that was written in French. Okay, but I think there's Science, Finance, and Actuary. And he also has working experience in Google in Sydney. So that's very, very impressive. And he is a very, very active researcher who already has quite a number of publications and working papers in various areas since completing his PhD. So without further ado, the floor is all yours, Patrick. So Patrick will talk about approximate Bayesian computation and writing performance Python code. Thank you.
Thanks, Eric, for that introduction. So this work, well, before I begin, I'll say the slides that I'll be presenting are accessible on this website here, slides.com, if anyone wanted to follow along. And the work is that the first half, well, most of the presentation is joint work that I've been doing with my colleague in Lyon University 1, Pierre-Olivier Goffard. So this slide is perhaps not necessary now that you've had such a great introduction, just mainly to say that my background, I do have some software engineering background and was in Denmark and Lyon. Now in Melbourne, I'm doing some slightly different work, this empirical dynamic modeling, which is not related, but to the practical aspect of that is that I've spent the last few months taking a large package written in Stata and rewriting it in C++ so that it runs a lot faster. So to talk about ABC, the algorithm that I'm going to present, I'll start with a motivation, the problem that we looked at. And it's an insurance problem. So we have a random number of claims, capital N, from some specific parametric model. And each of the claim sizes for that period are the U1 up to UN, all IID from another parametric model that we've chosen. And we want to fit these models, but we don't observe the whole data. Instead, we see some kind of aggregate of the data. So a basic one is the aggregate, the claims, the total number of claims that come in some period, or maybe we only observe X is the largest claim in a period, or the stop loss of the period, which is a kind of censored version of this total claims. So our question is, given that we have some sample of these x1 up to xn of these summaries, what is the theta frequency and theta severity, which best explains them? And this is quite a hard problem. And well, to give some real world application to it. Maybe this is a reinsurance contract. So the cedent is giving over some information to the reinsurer at each month, how much they need to pay out for the contract, but the reinsurer doesn't get to see all the claim by claim level details of that have happened in that month. And the reinsurer would like to sort of work backwards from their limited observation to try to have a better understanding of the risk that they've underwritten. And so I put here question one, and sort of easier question that we also looked at is basically if you observe these summaries x1 up to xn, but you also observe the number of claims which arrived in each period, then that makes the problem slightly easier. To set the expectations quite low though, this is almost an impossible question to answer. It's kind of like saying, this first question, it's kind of like saying, I have some numbers that add up to 10. What were those numbers? Well, of course, that's impossible. Or even this easier question is like saying, I have 3 numbers and they add up to 10. What were those 3 numbers? Still kind of impossible. So ABC is an algorithm, which I'll be describing, is used as a last resort when you don't have a likelihood. So, and I'll just talk about some scenarios where you won't have a likelihood. For simple random variables, we know what their likelihood is. A normal distribution is this bell curve and so on. But as soon as you start changing this up, making a model that's more realistic by combining simple random variables, then the resulting thing usually doesn't have a likelihood, as in we just can't do the math to find out what the likelihood is. And a really basic case is you add up 2 IID random variables, and then that sum, most of the time, the math just doesn't work. We can't calculate what that likelihood should be. Another case where you wouldn't have a likelihood is more practical. Say you have n observations and n IID observations, and the joint likelihood then is a product of each of the individual likelihoods. And if n becomes large, you're doing you're multiplying lots of small numbers together, and the computer often fails at this task and just gives you 0 as the answer. So in that case, we have an intractable likelihood. Or another way that this could happen is maybe you can calculate a likelihood, but the computer just takes so long to calculate it that your traditional MLE or EM methods just are not applicable. Even in these scenarios when you don't have the likelihood though, you can usually simulate random variables from these models. And by simulate, I mean the Monte Carlo simulate, as in create samples from these distributions. And that's what ABC utilizes. So the B in ABC is Bayesian statistics. I won't go into that, mainly just showing our notation is that we'll start off with a prior distribution is our best guess at what the theta should be before we even see any data. That's the pi of theta. And then we want to update that given some data to get a better idea what is pi of theta given the data. And that's the posterior distribution. So if you did have a likelihood, then you wouldn't do ABC. I'll just say that now. ABC is the last possible resort. It's the slowest algorithm to run. If you had a likelihood or something proportional to a likelihood, then just use MCMC. And there's libraries in Python and R that do it very well. Okay, so let's change tab. So to explain ABC, I've got some simple problem that is flipping a coin. So imagine that we flip a coin 3 times and we get heads, tails, heads as a result. And we want to work out what's the probability of heads for this given coin. The ABC way to do that is to just start simulating. So we start off by taking a random proposal theta prime here, and that's theta prime is 0.95, meaning that we're imagining a coin which comes up heads 95% of the time. We take that fake proposal theta and we just simulate some coin flips from it. So that's what I've got down here, H. So this coin gave us heads, heads, heads. We compare that to our observed data. And if the fake data that we just happened to create is different from the observed data, we throw this away and keep repeating this process. So again, we imagine a coin that comes up heads 40% of the time. You'd simulate some coin flips from it, and that doesn't get a match either. But somewhere here, we on our third attempt, we get, we're imagining a coin which is heads 54% of the time, and it simulates some fake data which happens to match the observed data. So we take this as one potential theta that could explain the data. And then repeating this process, so this animation will go up to 100 attempts. And I believe that about roughly 20 of them will collect one of these samples, and the histogram and the KDE here are of the thetas which generated fake data, which happen to match our observed data. So that procedure actually generates samples from the true posterior distribution. I'll call this the exact matching algorithm. I don't think it has a name because no one actually does this. And just to repeat what I was just showing, you have some observations, and you start off by generating potential theta which could explain them. And that is drawn from the prior distribution that you've chosen beforehand. Given that theta prime, then you generate some fake data, the x prime. And if they match, the x prime matches the observed data, then we store this as a sample, an IID sample from the posterior distribution. Okay, I can, of course, you can imagine that this, as soon as you start moving to more complicated things, this exact matching will fail. And even in this case, with just a really simple coin flips, if I have a large observation, so instead of I observe heads, tails, heads, I flip my observation is 8 coin flips, and which is what I've got here on the left, 5 heads and 3 tails. Then running that exact matching algorithm, well, we'll never, it's extremely unlikely that by random chance we'll pick a theta and it'll generate 8 coin flips that happen to exactly match our data. And this animation is showing after 100 attempts at this, we don't get a single match. So this is where the approximate part of ABC comes in. And so that is saying, if we generate some fake data and the fake data is not exactly the observed data, but it's pretty close, then we'll take that as a sample. We'll say that's good enough. So here, what the algorithm has done is it's proposed a theta, which is 0.55. So it's picturing a coin which comes up heads 55% of the time. It's done the 8 coin flips, and that's what's here on the right. And out of those 8, 6 of them were heads. And we'll accept that as being pretty close to our observed data, which had 5 heads. Again, next coin flip is another accept. That's imagining a coin 40% of the time heads, and then its fake data had 4 heads. And so there's basically in this algorithm, we're accepting if there's 4, 5, or 6 heads in the fake data. And letting this go on for 100 samples. I can't remember how many we accept, maybe around 20 something. Let's get to the end. Oh, nearly 30. So this is the ABC acceptance rejection algorithm. To get some samples from the approximate posterior, we repeatedly generate a proposal theta from the prior, generates fake data from that theta prime, and if the distance between the real data and the fake data is below some pre-specified threshold epsilon, then we accept it. So now the algorithm got slightly more involved because we need to specify what is close in terms of fake data to real data, what's an appropriate measure. And we also have to specify how close we're happy to accept. And the samples we get at the end, as I said, they're no longer from the real posterior, but they're from an approximate posterior, or the ABC posterior, which we can write down roughly what it is. But it's better to show a plot of what it is. How approximate are we talking? So this is for this particular data with the 8 coin flips. If we only accept fake data which has 0 distance from the real data, then this is what you get. This is the real posterior. If you accept an error of 1, which is what I showed in the previous animation, where we accept 4, 5, or 6 heads, then the resulting posterior you get is this orange one. And that's pretty good, really. It's this approximate version is centered basically on the true version, and it's a bit wider. It's not as confident of the answer, and that's a general trend. If you have less stringent requirements and you start accepting more and more, then the quality of your approximate posterior degrades. And then in the limit, if you accept everything, then it's no longer posterior at all. It's actually just recreating the prior that I had, which is this uniform on 0, 1. Okay, so in practice, I would say that the acceptance rejection algorithm that I just described, probably not very useful, but it would be better to use a sequential Monte Carlo version of the algorithm. And I won't go into the step-by-step details of how this works, but the main idea is to take a bad approximation and improve upon it. So it's kind of like in this previous step, starting with, say, this orange curve and then doing some computer work and then generating the blue curve and repeating this and getting closer and closer to the posterior. Okay, so let's look at some examples in practice. This is a test that we took inspiration from this paper of Garrido et al. 2016. And it is this case where we have claims come in, say, every month at a +1 rate, and the severity of the claims are dependent exponential. And by that, it means it's an exponential with the mean beta, but the mean is sort of adjusted by e to the delta n, where n is how many claims there are in that period. So in total, we have 3 parameters to fit: delta, lambda for the Poisson, beta, and delta for the dependent exponential. And we're not observing each claim by claim, we're only observing the sum of the claims in each period. So what I've got here are the ABC posteriors, the ABC fits. I'll work backwards from the prior. So the purple line at the bottom here is the prior distributions for the parameters that we specified. And we just set basic uniforms. And the blue and the green curves are what you would get if you only observed 50 observations in the blue curve. And the green curve is what you would get if you observed more, and you observed 250. So we can see the blue curves are a bit wider. They're not as sure as the answer, and they're not as accurate either. So the lambda, it's a bit off. But once you start getting a few more observations, the green curves are pretty much spot on these vertical dotted lines, which is the true values we use to simulate the data. Okay, so even just to compare against the true posterior, I mean, this problem that we're doing is hard, very hard, because we're only observing the aggregate of the claims. If you did observe all of the claims, then this becomes quite easy. You can just use Markov chain Monte Carlo, and that's what these histograms are, showing some MCMC histograms of the posterior. And the curves on top of them are what I had in the previous slide, the ABC version, which didn't have all that information. And we can see we're pretty close. Oops, wrong button. Okay. So let's see. Okay, let's hope this works. I'm on a virtual machine that we have here at the Melbourne Research Cloud with how many cores does it have? I think 80 virtual CPUs on it. And this is some code demonstration of the package that I created in the process of this work, ABC Re, which is short for, with a re is from reinsurance. We thought at the beginning that would be the main application. And I just wanted to show you it in action. When you run this sequential Monte Carlo method, it does this iterative procedure that I mentioned, starting with a really bad approximation and then moving on to better and better approximations. And on the right here is showing the core utilization for the server. So this is highly parallel code. It's using up all 80 cores of the server of the CPU. And as it gets down to the last iterations, it's using up 100% of those cores, because after each iteration, the problem gets harder, actually. You're being more stringent, you're accepting fewer and fewer samples. So it becomes a better candidate model problem for a parallel programming solution. And in fact, this took 45 seconds to do 10 iterations. And at the end of that, I got 1,000 samples from the posterior. And just in that last iteration, to go from epsilon is 1.9 to epsilon is 1.78, I had to sample, that's nearly 2 million proposals that I had to go through and reject most of them until I could get the 1,000 that I was happy with. So this is a very computationally demanding procedure. Okay, to show what happens when ABC fails, which is quite easy to see, we changed to a different model. We have data which is negative binomial frequency and Weibull claim size. And we don't observe the data, we observe the stop loss with a parameter 6, which is quite high for this data. And what it means is a lot of the data is censored. So instead of the 50 observations that we normally have, we in fact only have 11 which are non-zero. And similarly for the 250 case, only about 70 of them are non-zero. And the results below here are mixed to bad. I would say that this K parameter has done its fit the K parameter very well. The P, well, if you're very charitable, you would say that's a decent fit as well. But the alpha and the beta are quite off. And this is one thing that I've noticed running these experiments is that it often gets the scale parameters wrong in ways that compensate for each other. So here it's saying that the frequency distribution, the scale of it is lower than it should be, but then it compensates that by having severities which have a scale parameter which is higher than it should be, because it's just having difficulty disentangling if you're in the situation with lots of small claims or few large claims. But I guess the positive way to look at it is that if you would rather have the shape parameters fit well or the scale parameters fit well, I'd prefer the shape parameters to be fit well. And that's what it seems to be doing. It seems to be able to tell us that these Weibulls are very heavy-tailed and they have the K parameter is quite small. Okay, so in this case, if we also observe the stop loss, but we also saw the ends, which is how many claims happened in each time period, then, well, the problem becomes really easy for ABC to handle. It gets these posteriors, which you can barely even see the plots because they're so concentrated on the true values. Yeah, zoomed in. So one thing that can happen is you try to fit a model which is the wrong model. And I guess in reality, we never know which model, which parametric distribution generated the data. Well, that sentence probably doesn't even make sense, that real data isn't generated by a parametric model. And so here we took those negative binomial Weibull data and we tried to fit a negative binomial gamma to it. And it did as well as could be done in this situation, but more to the point, it's better to have a some kind of model selection. And that's another fantastic part about ABC. You get model selection for free in the algorithm. All you need to do is you need to say, here is a few potential models for the data, parametric distributions to try out. Here is a prior probability of each model. It can just be 1 divided by the number of models. And then the algorithm, you can choose one of these at random and then do the normal ABC from there. Given that I'm using this model, generate potential theta, from that generate fake data and repeat. And then at the end of the day, you get posterior model probabilities. So in the case of this exact example I was showing a moment ago, where the data really was coming from severities which were Weibull distributed, but we also wanted to compare against a gamma fit, well then ABC will, if it's only given 50 observations, it'll be about 70% confident that the Weibull model is the correct one. And then given 250 observations, it gets up to about 90-something% sure that the Weibull is the right one. And again, if you gave it the summaries and the number, the frequencies as well, then it's basically 100% sure that it's the right one. Okay, so the thing that I think is most impressive about ABC is it takes a problem, which is a hard statistics problem, and then it transforms it into a different domain altogether and turns it into a hard programming problem. And so that's sort of my segue to talk about different things to try out if you're trying to improve the speed of some code that you're writing, but in Python or R or any other language, any of these slow languages that are easy to use. Before getting into it, I would say that there's always this sort of a bit of caution to be had, that you should stop and ask, why am I trying to make some code run faster? There's this famous quote from Donald Knuth, who's perhaps the only guy who's famous in maths and computer science. Premature optimization is the root of all evil. So the way I would say to think about it is to compare heuristically about how much time you would take as a programmer, or your group of programmers would take, what's the cost of their time spent improving the code to run faster, and then compare that against how much time how much of the computer's time will be saved and how much that costs. And I mean, there's a lot involved here. I used to think that this right-hand side was basically zero, that I was not personally paying for the University of Queensland or the Aarhus University computers time, but in my new position, actually, we're mainly renting these large virtual machines, like on Amazon clouds, for example. And you see in a big red box, you are spending $20 an hour using this computer, for example. So in our case, that we can see this cost of the computer's time is actually quite relevant to our budget and how we use our money. Similarly, if the number of users who are going to run your code is greater than 1, which I guess we all hope is true. We don't really want to be writing code that is only run by us and never sees the light of day again. If the number of users is large, then it's worth putting some time in. So before talking about some other aspects of the computer, I just wanted to mention that there's 2 main ways that a program runs slowly. And the first one is related to reading and writing from memory. And the second one is related to just waiting for you have so much stuff for the processor to do that you're just waiting for it to go through all those things. So to talk about that a little bit, and just point out that inside a computer, well, for our purposes, there are two components. It's the processor, the CPU. I've got a little picture of an Intel one here, and on this random photo of a computer that I found online, it's the thing that's underneath this fan and heatsink, because it gets very hot and constantly needs to be cooled down. So that's the CPU, does all the actual mathematics of the computer. And then on the right here, we can see the red bars here, the RAM, the memory of the computer, where you'll be storing data and reading from data. And for our purposes, the only thing you need to know about RAM is that it's fantastically slow. Your processor can number crunch at some unbelievable speeds, but it's normally doing number crunching on some data that you have, which is stored in the memory. And the process of moving the data from your memory into the CPU to do the number crunching is a huge bottleneck. And actually, so a lot of programs are actually like this, where what they'll do is they'll be running for a while, and then they'll need to read in some data that it doesn't have access to, some data that's in the RAM. But because that is so slow, your operating system will say, okay, you can't do anything until you've got this data, so I'm putting you as a program to sleep. And then I'll wake you up again at some point in the future when the data is ready and you can keep resuming running. So in fact, a lot of programs on your computer are actually going like this, but they're actually running a very short amount of time and then waiting a lot of time. And not just waiting for data. I mean, if you open up your task manager right now, you'll see 300 processors sitting around waiting for you to click on the mouse, or waiting for you to receive a packet from the internet or something like that. But and so my point here is just to say that what I'll be discussing next is things that'll help when you're not in this scenario, when your data is not so massive that you're actually just waiting to read and write from it. Because that's usually the number one thing that's slowing down a computer. I'm just going to skip over the slide, but I basically, what I mentioned about there being a huge gap between reading from memory and then getting it into the CPU, well, computer hardware people have added these things called caches, and you can ask me afterwards if you're interested. But the one result of this is, if you have, say, a matrix, I've got a square matrix here, and if you're trying to calculate the column sums of it or the row sums of it, it's actually much faster to go in one direction rather than the other. And this depends on your programming language. So for Python, the row sums take, for this random test, 200 milliseconds, and it takes 500 milliseconds to go through and calculate column sums. And that's just a consequence of how this caching works. Okay, so the number one way to make any code faster is just to measure the speed profile it in a smart way. So I'll show some demo code that I'll be making faster in the next few minutes. This is taken straight from the ABC example that I mentioned before, where the code generates a vector of fake data from a specific model, where we have claims that are coming in at a geometric distribution, and the claim sizes are exponential. And this function will calculate this sum here, capital T times. So this function needs to get called, as I said, like a ginormous amount of times. So we want this to be optimized. Let me see if I can change to the right tab again. So with Python, there's a beautiful tool that you can use, which is if you just put this % heat above some code, what it'll do is it'll run the code and generate a line-by-line description of how long each line took. So you can say UN, here this function is sampling geometric exponential sums, and for each one it spends a bit of time generating the frequency and spend a lot of time generating each of the claim sizes individually. So this is one useful way to get a feel of where your code's spending time. But a better way is actually my favorite. Is another tool in Python called snakeviz. So similarly, you just put this few words, % above your code. It'll pop up a new window which shows you how long each function took, and then how long the functions that were called by this function took. So here is our function sample geometric exponential sums. And inside that, it called you can see maybe on the left in small writing, RVs function. So it's calling this sample random variables function. And that takes 10% of the whole time. So this is an indication that something is wrong. We thought that the sampling random variables should take most of this function's time. So what is the rest of the time being spent on? It's 90% is being spent in some function that we don't really, looks like garbage, some distribution infrastructure thing. And then going down to seeing what that's actually doing, it's actually constructing some documentation. And so it turns out this is actually something, I didn't make this example up, this actually happened to me. There's two ways, at least in this Python library, to generate random variables. And one is here on the left, stats, and then dot distribution name. And then the parameter, then .rvs. And then the other way is stats.distribution name .rvs, and put the parameter in there. And that turns out that moving from the left to the right one goes from 1.7 seconds down to 89 milliseconds. So doing a little bit of profiling and just asking the question, like, why is it spending time here and is it necessary? I get 20 times speed up directly. And I mean, further looking around, I could see that this whole library I was using called Scipy, it was just, at the end of the day, it was just calling another library to generate the random variables, which is numpy. So I just skipped the middleman and going straight to numpy to generate the random variables. And that again produced another 16 times speed up for the code. Okay, then vectorized code, I'll just go through this very quickly. So here we've got lots of for loops, and one general rule is for loops are not very good. Here, what I can do is, instead of doing everything one by one, instead of saying, give me a frequency sample, give me a claim severity sample, you can try to do them sort of in one hit. I'll say, give me all the frequencies for our whole time period, and then go in and each time give me a block of claim sizes. In fact, this version of the code is more vectorized, but it didn't improve the runtime. I'm not sure why. But then another version of that is to do all the random variable generation in one huge hit at the beginning. So say, give me all the frequency random variables in one hit, and then give me all the claim size random variables that I'll need for the whole time period right after it. And then do the process of going through and creating these X summaries from the raw data afterwards, and that gets a 2 times speed up. Okay, so on to a topic that a topic in the library I'm most impressed by, which is numba. So I'll be talking about compilers just briefly, and mention all these graphics that I got for the next few slides are from this blog post by Lynn Clark, Crash Course in JIT Compilers, and that's a really well-written blog post. If I would recommend you all take a look at that. And this particular graphic is saying, like, at eye level, what is a programming language? And it's, you have a computer and you want to talk to the computer, in something you understand, and they have a different language. The computer itself has a different language, kind of like this movie Arrival, where the aliens come and they land and they send out people trying to teach them English so they can even talk to the aliens. So that's sort of like what's going on here. And there's two ways to do this, and two ways to write to do programming, which then gets turned into instructions for the computer. Python and R and many of these slow languages are actually interpretive. That's what the graphic on the left shows, and basically that means that the Python program itself looks at your code line by line, and for each line it spends a bit of time thinking about it, translates what you wrote into machine instructions, and then runs the code straight away. So it does each line, it moves on to the next line of your code, thinks for a while, and interprets it into instructions for the computer. And the alternative to this is what was like done in the early days of computers, was the only option is to compile. And that is what it looks like. It's saying, takes your whole program in one hit, thinks about what the whole program is doing, and generates a whole huge program for you, generates all the instructions that the computer needs to run, to execute your program. And I'll simplify things by saying that the second option generally creates faster code. Well, faster code to run. These compilers are somewhat famous for taking a long time to do their job, actually, to actually do the compilation step. But the nice thing about that is that you're only wasting the programmer's time waiting for compilers to run, but you're wasting the user's time when you're running interpreted code. When it's constantly interpreting things over and over again, the user's time gets wasted. So to briefly have a little comparison of some reasons the interpreter or the compiler creates fast or slow code. I've got an example here, which is both in Python and C++, really basic. We're saying x equals 1, y equals 2, z equals x plus y. So in Python, that's perfectly fine. It'll calculate the number 3. And then later on, if I also change x to be a different type altogether, it's no longer a number, but a string, and y is also a string, and I add them together, that'll create another string, which is Patrick space lorp. It'll do string concatenation using the same z equals x plus y code as above, where it was just doing normal integer addition. The C++ version is slightly different. You have to say, I'm talking x is an integer, so I have to tell the computer what is the type of each of my variables, and x2 is a string. And similarly, I can't just, I had to give this a different name, x2, y2, z2, because in C++, the compiler is not letting you just take a variable and change its type willy-nilly during a function. If you say x is an integer, it's always going to be an integer. So let's take a look at what happens quickly. So this is a tool called Compiler Explorer. So what it does is you put in C++ code on one side, and it compiles it to individual instructions for your processor on the other. And so we can appreciate how here the one line of C++, this x equals 1 line, turns into one instruction for the computer. So see, when you're at this level, you're already making your code translates to very efficient computer machine code. And the only complicated thing here is that the addition, that one line of C code gets turned into 3 instructions. These run extremely quickly. But this is a bit of a lie, actually. If you were to normally do a user compiler, you would let the compiler optimize the code. And so that's what this -02 is doing. And in fact, what it does is it turns these instructions, these C++ instructions, into 0 computer instructions. In fact, it sees that you can see the whole picture of your program. It knows this Z is not going anywhere. You're not using Z anyway. So why bother even calculating it? So it takes that chunk and just throws it out. And that's one very simple optimization that the compiler can do, because it sees the whole picture compared to Python, which is just reading things line by line. It doesn't know what's coming next. Okay, so on the other hand, let's see what Python is doing. So this is a tool where it lets me look at a bit of Python and see sort of what C code is actually being called underneath when you run the Python code. So this is quite basic. So x equals 1. Well, it's not super basic, but it's calling some function to generate x. And if there's an error, then do something about it, and same for y. But look at how much wasteful code is being done here. If you're just adding up two numbers, it needs to get the first, get x. If that had some problem, handle the error. Count, tell Python that I'm using x now, and this is using reference counting, which is called. Do the same thing for y. And then instead of just doing a normal addition, there's a pi number underscore add function that's being called. And basically, I'm just trying to say that Python is not slow because the computer starts running more slowly when it sees that it's running Python. It's just that Python is doing a lot more stuff. So I can see that I'm running over time. So I'm trying to blast through some of the last slides that I have. One other point here is that in Python, say we have this function arraySum that takes in an array and just loops through it and tries to give me the sum of that array. Then Python is wasting a lot of time checking the types of everything. It'll say, Python has to say, is sum an integer, and do something and handle the code differently if it's an integer or not an integer. Is an array still an array? Is I an integer, and so on. And then does the next line of the for loop, and it does the same checks over and over again, because it doesn't know whether in the future you're going to change the type of this thing underneath, sort of in the process of the code. So to get a compiled version of Python, it sort of needs to know the types of your variables. The really dirty way that I wouldn't recommend is to actually use this thing called Python to tell Python this thing that I'm working on is a double, this other thing is a long, this other variable is a double. But a better way is actually just to use the library called numba, and it does, all you need to do is take your original code and add these 4 characters in front of it, ngit. And what happens then is it'll wait for you to call this function. And the first time you call this function, you can just look at the things that you gave it. You call this function with an integer in the first parameter and a floating point number in the second. So it doesn't need to guess the types. It just waits for you to call the code, and then it can see what types are going to be used. And then during that first call, it's a bit slow because it will compile your Python down into very fast machine code. But then the second time you call this function, it won't recompile. It'll just use this compiled version, which is much faster than the Python version. So adding this ngit here moves the speed of this function down from 2 milliseconds to 100 microseconds. So another 16 times speed up for really no work at all. Now, putting all that together, the original code took 1.7 seconds. Doing a little bit of profiling, a little bit of vectorizing, and just putting that ngit in front of the function, in total is a 10,000 times speed up. And that's not even making the code parallel. And say you made the code parallel over 80 cores, you wouldn't get an 80 times speed up, you get something less, maybe 50 times. And overall, we're talking a 50,000 times improvement in speed. So I have some slides that I've run out of time, so I won't talk about parallelizing the code, but I just show you very briefly that if you're using Python, I'd highly recommend this library JobLib. This is how you take some code that runs in serial and make it run on multiple cores. It's really makes the process really quite straightforward. So our paper that this is all related to is being resubmitted at the moment, and will be adding more and more complicated examples to the paper, and we've had some small theoretical contribution. Also, this package that I've been talking about, this Python package, is online. That's another contribution, which is mainly what I've been focusing on. And to finish up, my take-home messages for you would be, I hope now that you've seen this talk, you know what ABC is and when you can use it. So by that, I mean it's applicable in nearly every situation. You don't need to be doing insurance, reinsurance applications. You can use ABC for everything. But when should you be using it? And that's when every other option doesn't work. It's a very inefficient method. Use it as a last resort. ABC takes a statistics problem, turns it into a computing problem. And if you're doing some kind of trying to make code run faster, particularly Python code, then profile the code. That's really the number one thing you can do to make it faster, because most of the time it's really wastefully calculating stuff that you're not expecting it. You don't think it's spending its time in one part of the code when it really is. Vectorizing the code, try to compile the code if possible. It'll get rid of some of the inefficiencies that are built into Python or any other interpreted language. And then parallelize the code as a last step after you've done all this. But make sure not to overdo it. It's easy to add some parallelization, and then actually your code runs slower now that you're using 80 cores instead of just doing things on one CPU. So I'll stop there. Thanks very much.
Thank you, Patrick, for the very, very interesting talk. So we would like to invite the audience to raise any questions or comments. Yeah, if you have any question or comments, you may type in the chat box or you may unmute yourself. If there's no question yet, maybe I have a question. It's not really a question, it's maybe more like a comment. So actually your the time spent in each each part of your when you talk about the programming, right? When you have various command and then you show the time spent in like each section, right? By the code. I think that is very interesting. Although I'm not using like Python or C++, I'm actually using Mathematica. So actually because it's easy anyway, Mathematica is very, very intuitive. Although it may not be the best programming software. So I actually encounter very, very similar type of, I won't say problem or issue, I encounter, similar type of things in the sense that, for example, in some of my research, I need to solve, like, for example, 1,000 linear equations, let's say, right? Then I need to input the coefficient matrix, which would be like 1,000 times 1,000, which would be like 1,000,000 entries. So in Mathematica, I can also time I can also ask Mathematica to give me the time spent in a certain command. So what I found is that it actually takes much more time for Mathematica to put those numbers into the matrix, right, with 1,000,000 entries. That takes actually much longer. It can take a minute or so, okay? But to calculate, for example, let's say the determinant of the matrix, for example, after you have input those entries, it's actually really, really quick. Yeah, so I think that is somehow a similar issue, right? I think when you input those numbers in those 1,000,000 numbers into the matrix, right? I think it takes time for for the RAM to work, right? It should sort of, the numbers should be entered, right? It's written into the RAM and so on, right? I think that is similar issue, right? Do you think it's similar?
Yeah, definitely. I spent a long time using Mathematica actually, and the reason I moved off it, there was one paper in particular I thought we'd use Mathematica for a short bit of programming, and my colleague didn't know Mathematica, so I thought, oh, okay, I can just do this short bit of programming, and that short bit turned into a bigger bit of programming, and then it ended up being thousands of lines of Mathematica that I was trying to maintain, and and my colleague had no interest in helping because he didn't know the language at all. So this is why I don't use Mathematica anymore. I try to stick to the languages that are at least everyone in my team can get on board with and fix bugs or follow along. But with Mathematica, it was, yeah, I was sort of addicted to it because it has such really nice high-level things built into it for probability theory and so on. But it hit a lot of things underneath, like, for example, if you were simulating random variables from like a y-ball distribution, and you said, give me a random variable from this, it would sometimes switch algorithms underneath. So if you were saying, give me a y-ball distribution conditioned on being less than 10, it'll use one algorithm, and then conditioned on being greater than 10, it might use the same algorithm. But if you moved it up a bit and say conditioned on greater than 100, then it must switch something internally, and it would suddenly take 100 times as long to do that. And so I gave up after a while because I couldn't see inside what it was doing, and it was doing this kind of thing, but where it was doing drastic changes to the implementation. Then I had to give up eventually on it, because at least with Python, R, and so on, it might not be easy, but you can always look inside to see what is it actually doing. Like MATLAB and Mathematica, those closed source ones, and it's hard to optimize because it is such a black box. These profiling tools just won't tell you much information.
Yeah, thank you.
Yeah.
Any more questions? Yeah.
Sorry, I have a very quick question. So I don't know much about reinsurance, but do insurance companies often want to analyze the underlying insurance data, or do they just primarily analyze their input, which is the reinsured data that was by the insurers, because they mainly work with that? So they really need to analyze the underlying data from the insurance company? Yeah, I don't know if I make it clear.
Yeah, I see. Well, this is frankly a question that I think this audience would probably know the answer to better than me. Like Pierre, Olivier, and I have been trying to think of like great real world use cases for doing some kind of like statistics where you don't have a likelihood. And that's the example we came up with, where you're observing not the whole data, you're only partially observing it. I don't have a great deal of understanding what a real reinsurer would do. Maybe they would have different requirements in Australia to the EU, to other countries. But I guess that once the contract has been set up, the cedent wouldn't be handing over the entire claim-by-claim information every month for the whole period. They wouldn't keep, even if there was a lot of requirements to set up a contract, they wouldn't continually have access to all that data, because that's very valuable in itself. So perhaps they have some requirements to set up the contract, but maybe over time they want to check, are our assumptions still valid? Should we be increasing the price of this contract or so on? Maybe this is a situation where the scenario I described is relevant.
I see, thank you.
Thanks.
Okay, any more questions or comments from the audience? Okay, so if not, let's thank our first speaker of the year, Patrick. Let's thank Patrick again. And yeah, and then I think we can continue to have some relaxing discussion in this so-called like a tea time, where I think the audience, if you would like to stay, you can grab a cup of tea, or you may have some brunch if you want. Yeah, and while we can have a casual chat. I think Ji-Wei, could you please maybe just stop the recording of this? Yeah.
Yes, I'm starting.